So this is detecting workload anomalies with Prometheus and machine learning. We'll get into all of that throughout today. Sponsors are awesome. I've probably talked to all y'all this week, so thank you for your business. And then thanks obviously to all the sponsors for supporting the event. That's what helps keep this thing alive outside of the community, which is super duper awesome, which really keeps this thing alive. Anyway, I'm Anthony Nocentino. I'm a principal field solution architect at Pure Storage. Almost said Centino Systems there. It's been a while. I specialize in system architecture and performance. I like to make computers go fast. That's my job, right? I get to work with some of the biggest workloads on the planet from a high performance standpoint, both in throughput and latency. And it's the main reason why I stopped consulting to go work at Pure, is to have access to problems like that. And so we'll get into a whole bunch of stuff about what I did to apply this stuff at work. Anyway, like I said a few minutes ago, I didn't intend this to be a hands-on lab, but since my partner in crime, Joe Hughes, is doing a hands-on lab, I took that as a challenge. If you want to follow along, go ahead and pull this repo here. All you have to do is have Docker on your laptop, and we'll walk through the rest. That's kind of the idea. I love using Docker to help hand a solution over to a learner or a customer or whatever, because, well, it works on my laptop. Now it's going to work on your laptop, all right? So we're going to start off with what Telegraph, Prometheus, and Grafana are, and kind of the architecture behind that. And then we'll get into building an anomaly detection model with machine learning, and we'll talk about some practical use cases for this solution, right? And I think the biggest question is, why did I build this? Like, why do I want to use machine learning, other than like every earnings call talks about machine learning and AI, and it will help stock prices? No, I'm kidding. I get to work with a lot of customers at work, and even when I was a consultant, that just don't have monitoring systems. And that was the nexus of this project that I built in Docker Compose, because I want to be like, hey, look, you have a monitoring system now, right? It's kind of nice to be able to do that. And we're going to do this in code today. But then I found customers had a hard time, and I made a living off this as a consultant, of defining what's normal and what's not normal from a performance standpoint, right? Well, I want to know if things are running too hot or things are running too cold, and be able to answer that question. And so I want to add a couple disclaimers, as anyone who is in here is cracking open the code or looking at my code today. As I get into this, is number one, I'm not a data scientist. And number two, I'm not a professional developer, right? I've never written production grade. Well, I used to write production grade code, but it's been about 15 years since I've done that. But I had a problem that I wanted to solve, right? And so I took some of the things that I've built with Grafana and Prometheus and all of that, and I augmented that with machine learning. But as I said earlier, I'm not a data scientist, so I wanted to go find something off the shelf to use to help plug into this platform so that I could do the machine learning stuff that I wanted to do predictions on the data that's coming into Prometheus and Grafana from our systems. So first and foremost, I want to define kind of the scope of the project in terms of like, what is observability? Like, why do I want to do these things within a platform? And I want to, again, understand the health of the system, and usually that's rooted in performance. And performance meaning, I want to know, again, what's normal, what's not normal, and quantify the system that I'm working on: CPU, disk, RAM, things like that. I also buckle or couple in availability as part of this as well. Also, performance, I think, is an availability concern as well, because if I can't run a query or hit a web server because it's saturated, I want to be able to know those things, because the next user that comes along can't do the thing that they need to do in my environment, right? Load a patient record, buy a book, whatever it is that the business does. And that's what's next. So when I'm building monitoring systems, I focus a lot on application behavior. What's the system actually do, right? Is it about loading patient records? All right, well, how long does it take to load a patient record? That's a critical metric in a system. A doctor doesn't care about what the CPU utilization is on your server. Absolutely not, right? So as you build a platform for monitoring, take those things into account as well. Transaction throughput in a database is a big deal, because that tells me how fast things are occurring. But what really matters is when the user clicked OK to buy the thing in the shopping cart, how fast did that occur? There's a metric that I found last week from Amazon. It's a little old, but they basically correlated 100 milliseconds in latency on a web page cost them $1 million a day, right? So this is real stuff to a business. I have lots of stories from my consulting days about businesses that had really slow systems because of some esoteric configuration thing in the corner that no one really thought about, that you break that bottleneck down and you get 10x performance improvement. So as you're building systems, focus on what the system actually does. But obviously as nerds, we like CPU, disk, RAM, all those good things that we get into. And so that kind of goes to the next point, is focus on the whole stack. Today we're going to focus on a metric because this is kind of a proof of concept system from a learning standpoint. I want to show you how it all pieces together, but focus on the whole thing, right? For years, I talked about building, highly available SQL Server systems, and what I would say to students and the customers, like, nobody cares if SQL Server is online. They care if they can go to the web page, buy the thing, load the thing, which executes the transaction, it reads from a database, right? Focus on the whole stack when you're building a monitoring system. Super duper important. Think about the whole system, right? Not just a server or service, but the whole system, and also expand that out to the whole platform. What's the whole organization doing? Building dashboards that expose that information is super duper important. Cool. All right, so this is kind of the core architecture for kind of the Prometheus Grafana stack, where we have the source system, right? That's the thing that we're going to get performance data from. That feeds into a data collector, or actually the data collector goes, reaches in, pulls that data out, sticks it in a data store, which then becomes visualized in some way. And so this system that we are going to build today is going to read from SQL servers. It's going to stick that data, or that data is going to be read out of SQL Server via telegraph, and we'll get into what that is in a minute. It's going to stick that data in Prometheus and then visualize that in Grafana, right? So that's kind of the core components of this monitoring stack. And we're going to deep dive into each one of these buckets after we look at the cutest logo in IT, right? So this is the Docker Compose logo. I used to say it was the Docker whale, but then I got involved with Compose and I was like, well, that's adorable, right? So surprise, I built this system on containers. And the idea is with Compose, if you're into the code right now, you will see that I can define those big buckets that we just saw in the application and give it to you to run. All right, and all you have to do is run one command because of what Docker Compose does. Docker Compose will start up all the containers. There's actually one in there that'll be built because it's going to inject the Python script that we're going to do together today. Builds that container as well. Configures all the applications, deals with all the networking stuff, so you can kind of abstract that behind the curtain a little bit. Exposes Grafana to the real network, right? So we can hit it from other systems. And it all happens behind the scenes because this is all going to be orchestrated in code that you can run anywhere you have Docker. In fact, I run the same system on this laptop in Docker Desktop, and I run it in a data center just on a Linux, on an Ubuntu machine running regular old Docker as well. And so it's up, running, and persistent. So the config that I have in here, not to say that it's like super duper robust, but I'll talk about some elements that'll make the configuration persistent between reboots and crashes and things like that. Not that my code ever crashes. And it can run, I just covered that point. It can run anywhere you have Docker. So, all right, so that's phase one. Any questions or comments, team? Everybody excited for monitoring and machine learning at 9 o'clock in the morning? Yeah. Was it a blessing in disguise that like the party was canceled last night and no one stayed up too late? Yeah. Was for me, because now I didn't party last night and I can party tonight, right? So I told the organizers, it's good for me, bad for y'all. Anyway, so telegraph, what's a metric? Let's get into that. Generally speaking, it's going to be performance data, but I really want to make sure that we understand it also can be other elements to the business. I've worked with customers to instrument actual code as well to emit data, again, to get around things like business level transactions. I had a customer that it's a truck stop scale weighing business, and we built a bunch of metrics in their code to help understand failure conditions on their scales, how fast trucks were moving through a scale and things like that, which is a fantastic joke when I talk about performance. I'm like, well, it's only as fast as it needs to be to get an 18-wheeler on the scale and then off the scale. They're like, yeah, but do that 100,000 times an hour. I was like, oh yeah, okay. So think about the business. Telegraph has a bunch of plugins. We're gonna focus on SQL Server today, and we're gonna look at some of the other ones in a second. Telegraph has the responsibility of collecting the metrics from the thing. So you don't have to be a SQL Server pro to write DMVs or to hit perf counters. You can just configure Telegraph to go get that for you, and it exposes that over an HTTP endpoint. So we have in this system that we're building today, we're gonna have a bunch of SQL servers. Telegraph's gonna start up. It's gonna read a bunch of DMVs, which are ways that SQL Server can expose performance data to you. And then that's going to be exposed as what's called a metrics endpoint, right? So it's an HTTP URL that you can hit that looks like this. And so we'll have just a web page that runs. This will be in the container implementation that you have right now on port 9273, where it will have the metrics exposed to you to read. And so there's the URL you can hit. We'll focus on that more in a second. And then there's some individual metrics that are exposed. So SQL Server CPU, process CPU is the metric. On the right here, we have some tags. So host equals Telegraph, which is the actual host that's running Telegraph. The type of measurement, which is a tag added by Telegraph. And then it also adds a tag for the actual SQL Server instance that we're looking at. So that's 2 measurements at that exact point in time when that page got loaded. And you can tell it wasn't doing anything, right? 0% CPU. And so that is how we're able to get that data out of a SQL Server into Telegraph. Other Telegraph plugins that will probably be interesting to you are these, right? You can hit operating systems like Windows or Linux. We talked about SQL Server. The VMware one's pretty good. I haven't used the MySQL one, and there's a whole slew of other ones out there. Any questions or comments about Telegraph, team? What's up? The question is, am I using Telegraph for persistence of the data that's being pulled from the system? It's more about getting the information from the system. It's the metric exposer, right? So certainly we could have, if you think about what we're doing here, is we're putting the data in a format, in a universal format, right? This is what open metrics format, I believe, is the standard here. And what we're doing is we're exposing the data in a way that other systems know that it should be. It's like an interface in terms of software development. Otherwise, we'd have to teach every Prometheus data store how to talk to SQL Server, which wouldn't be fun, right? So this is kind of the middleware that is the bridge to expose the data in a unified way. I'm going to use this pattern in the machine learning stuff in a little bit on how when I start to do the analytics on it. So you'll see this pattern again, kind of following the same organization. And we'll look at, there's a software library that we're going to use that helps us get this structure. So it's more about the exposing of data in a uniform interface, right? Good question. We'll talk about persistency right now. So Prometheus is a time series database that stores stuff, and we're going to put metrics in there. And so what we'll do is it's a time series database that stores the collected metrics. And what Prometheus will do is we'll define jobs that on an interval will hit that URL, okay? And when they hit that URL, it's going to ingest that data and store it persistently in Prometheus, right? So that we can come along later and query that data with a thing called PromQL, Prometheus query language, right? And so that's the interface to get the data out of Prometheus. And so what happens we'll look at this in code in a second, is we define jobs in Prometheus that hit that endpoint, pull the data out, and then stick it into Prometheus. And then that job runs on a schedule, right? So that's our sampling interval. And then we'll have those samples over time to look at. And so in the Prometheus web interface, the one that you'll have in this implementation, this is kind of the administrative interface to work with Prometheus directly. And so what I've done here is I've gone to that URL, which will be available in your labs. And I went and I asked for the metric, the one that we just saw on the previous screen, right? That's the actual value. And then I want to go after a particular tag. If you remember, there were 2 before, right? And so here I'm scoping the query to just instance over a time vector of 1 day. And so what'll happen is it'll pull the data out. So this is in the database, data store. And these are the values available at that exact point in time. And then I can take these and we'll do other stuff with them. And so as that data flows, we hit SQL Server, is hit by Telegraph. Telegraph is hit by Prometheus, which stores the stuff, right, for us to use over time. Any questions or comments about that, team? We good? Yeah? Everyone thinking about the party tonight? Oh, and then there's like any other query language, you can get as zany as you want, right, with regards to how to do it. Today, I want to keep it pretty simple in that space. On the Grafana side of the house, Grafana is a visualization tool, which is a fancy way of saying it makes dashboards. And it goes and it has the job of reading the data out of Prometheus to draw the visualizations, right? And the real value to that is it allows us to see trends over time, right? Because we're good at looking at pictures. What's the expression? Is like a picture conveys 1,000 words. Yeah. Anyway, so that's what we're going to get as an end result. So what we have here is CPU over time for a particular instance, and this is about a 24-hour interval. And I'm interested in values like mean and last and max over the sampling interval, right? So I have an average, I have a min and a max, but that really doesn't tell me a lot about what's going on in that system. It's just kind of a discrete metrics to visualize. So the flow looks like this. We'll define in Grafana a chart like CPU, or write a query, which will go and pull that data out of Prometheus and draw a pretty picture, right? And then we hit that over a web interface. And so let's go ahead and do these things together, right? We're going to start at the monitoring stack. We're going to see how metrics are collected and exposed, access a couple of those, and then look at it in Grafana. Cool. All right. So once you pull the code down, you'll have all of this stuff. I'm currently making my laptop really, really sad, but it's a MacBook Air, so it doesn't have a fan, so I don't know exactly how sad it is right now. But it's sad because I want to have some workload running because I'm collecting metrics off of this laptop, right? And so I started up the monitoring stack here. So let's go ahead and look at that code. Oops, maybe I got to break out of that. Well, also, if you notice, I called the script CPU sadness. So really, it's that sad. So in Docker Compose, you have this thing called a service. And on the left there, I have it all collapsed. I have Telegraph, Prometheus, Grafana. I have the metrics ML thing. We'll talk about that later. And then I have 2 SQL servers up and running. And so these are services. These also are DNS names inside of Docker, or in Compose inside of the network. So I can address these elements by name rather than IP address and port, and it manages that for me so I don't have to worry about it. So when I'm looking at a particular service, I have a thing like, I have to use a platform because this is a ARM processor, but it's running on AMD, and it's pretty cool that that actually works in this year. I'm running a particular image, give it a name, accessible port, and have persistent data and some environment config. But this isn't about containers. This is more about showing how this individual implementation comes together. We'll go into our Telegraph implementation next. It's using the regular old Telegraph image. We're using depends on Prometheus, so this service won't start until Prometheus starts. I have some configuration data that I'm injecting here. Restart on failure means if this container crashes, it'll restart it. If the system reboots, it'll restart it, which is pretty cool. And I'm exposing it on a port. The left-hand side is the port available to me outside the container, and then the right-hand side is the port inside the container. And so that's how we're able to hit that. So here's the Prometheus config. Again, we're injecting some configuration, 60 days of retention. This is where the data actually lives. And this is the configuration file for the things like the scrape points, which we're going to talk about in a second. And then I have persistent data, and I'm injecting the configuration from outside of Prometheus. And what I mean by that is this, if you're not familiar with this concept, in a volume, I can expose an external file internally into the container. So this file here physically lives here on my file system, right there, okay? Like that actual file. Because of the magic of Docker, it exposes that file to the container at this location, which is where Prometheus is looking for its configuration, right? And so that's why you can control the configuration of this outside, and then that's how it gets inside the container. And that also gives us the ability to delete and recreate containers without having to worry about configuration. And then next is, we did Telegraph, Grafana. So with Grafana, one of the things I did in this project is saved you from the luxury of having to configure where your data is coming from and a very basic dashboard. And so that's what we have at the bottom here. I'm injecting some configuration so that it'll create the data source for you and create the dashboards for you. So it just works when you start it up, right? And similarly, injecting some config using the default username and password to get into the Grafana interface, which we'll look at in a second. Cool. Any questions or comments around Docker Compose team? It's magic, isn't it? Love it. All right. Docker, let me see. I think I already have Docker. Yes. Yeah, everything's already up and running. But to start the monitoring stack, Docker Compose up, -- detach, and then boom, everything should be up and running. Oh, look at that, I had Docker PS right there. I've already started the workload of adding some sadness to the CPU. So what's happening here is I copy this file into the container, I exec into the container, I kick off the CPU sadness script, I leave the container, and this is what you saw a second ago when we walked in, is that right there. So just to see how hot that system is. This particular workload will blow out my CPU to 1,000%. So I had to suppress it a little bit. So that's what that line is right there. It slows down the workload from a Docker standpoint so that, well, my CPU on my system is not 100% utilization while I'm trying to teach today. Cool. Any questions or comments around Docker team? Compose, configuration files, good stuff. Awesome. So let's look at some metrics. So these are being collected right now, right? So if I go and I look for SQL Server, CPU process, let me grab that, paste it down here to highlight it. We can see that those metrics are coming in real time, right? So there is the CPU utilization as viewed by SQL Server, right? You might be thinking, well, it was 500% in Docker. That's how Docker quantifies CPU across multiple CPUs. This is a rolled up metric inside of SQL Server across all CPUs, capping out at 100%. And then we can see the other instance is just kind of hanging out here. And there is all of these metrics if you want to get super geeky, and it just goes on for days, right? Yeah. So the question is, if I refresh, do I get new data, right? Yeah, so there you can see it doing it real time. And that's, so if I go down a little bit, where is G62, this is going to be really stable because the workload's super stable. So, but to answer your question, sir? Yes. Yeah. Right, we're going to get to that piece in a minute. Yeah, the comment is, does something have to be regularly collected to get the data? And we will cover that in a second. But good question. Ooh, I can't show that yet. Shh. Okay, so just a real quick look at what Telegraph brings to the party. We're going to focus a lot on SQL Server, but there's many different plugins. The plugins then have their own configuration. But in this lab, here you can see I have the 2 SQL servers that are up and running, and we're just hitting those to grab their performance data. And I'm also pulling in way more metrics than I need to, but we can, so in this specific implementation, and if you get into VMware one too, there's a gazillion and 1 metrics in the VMware implementation. So you're going to want to scope that down to the things that you're interested in for a couple of reasons. One, when you read all the metrics, it can put some pressure on vCenter. And 2, it's a lot of data to store. So don't bring everything, right? Bring what you need and then expand it as you need it. And so that's kind of the big takeaway here, is you have to configure what you're monitoring and then how much of the stuff that you're monitoring. And that would apply to any of the plugin models that Telegraph uses. So this will answer your question directly, is how do we get the data, right? And so that's what we have here, is we have a scrape endpoint, a global configuration of how fast I want to sample. This is every 30 seconds. And so the first one is hitting, it's a scrape config with the job name of Telegraph, hitting the metrics endpoint. And the target is the DNS name of Telegraph, which was the Compose service on that port. And so this will hit that thing every 30 seconds and take a sample, all right? Ignore the bottom one, we'll come to that one. We'll get back to that one in a minute. And so that's how the data is refreshed and then stored, right? So this is Prometheus, is literally its job, is to sample and store that data. Cool, leave that one open.
So,
uh-oh.
just a second. No.
What's up, buddy?
Does Telegraph query SQL even if Prometheus doesn't query Telegraph?
Does Telegraph query? Does Telegraph? I'm like 99% sure it is sampled when the page is drawn, and that's how I implemented my side. When we get into the stuff that I did, I hit when the page is drawn, the metric is sampled. But I'll double check that for you. But yeah, I guess we proved that because we refreshed it and we were seeing new data.
That's what I was suspecting, but it wasn't what I expected, and that's why I asked.
Yeah. Cool. It's a good question. All right, so let's go ahead and run a query. When you get into the Prometheus, it's going to be on localhost 9090. You'll land on this page by default. And it does a really good job of navigating for you. You'll spend a lot of time in here because you got to navigate the data to figure out what's important to you. This is where you'll craft your queries to figure out how you want to expose the data to other systems. And if you hit this little globy thing here, you get explorer of all the metrics that are exposed. And we are focusing on SQL Server CPU, which will be that one. So if I run this here, it's going to return everything from the last sample interval for all of the hosts that are on the system, right? So there's no parameters in the query there to go get stuff. And so there we see the two, the one that's running hot and the one that's running not so hot. And if I wanted to go and get a specific instance, it does this great job of auto-completing equals, and it'll tell you, you can do a not a wildcard match, but a partial string match or a quality search. And I want to go after, and again, it completes the host for you. Then you can scope your query down to limit that, and then add a time vector on the bottom. So if I do last 3 hours, whatever that is. And so you can see it's going to give me, zoom out. So I hit it, it's going to expose all of that data to me over a range of time. That's the last 3 hours of samples every 30 seconds, right? So we can see this is the Unix time since epoch, which will convert later. And then we have zeros, and then you can see things get spicier as we move forward in time. So 9%, 62%, things like that. And so that's how those metrics will be exposed back into the platform. From a Grafana standpoint, so now we have sample data in a data store, and I want to get access to that data in Grafana. So that's kind of the last piece of the puzzle. You don't have to configure this. Again, it's part of the Compose implementation to inject this configuration, but the scrape, Grafana will hit the Prometheus endpoint to read the data, right? And so this is what's happening behind the scenes there to expose that to you. And so let's go ahead and launch this page, which is going to be localhost 3000. And so again, out of the box, if you scroll down to the bottom left here, you have 2 dashboards in the config. Look at the basic one first, and you'll see when I started the workload, basically when I opened my laptop up this morning, and then things got hot for this particular system. We'll look at real workloads in the presentation, so don't worry about that. And so for here, we have a couple of things going on. Let's see, what I want to get into first is how this thing got drawn. Is I added a new visualization here, which then gets you this screen here. The data source will be pre-configured, so if you want to just click that, but I've already done that for you here. That comes in as part of the config, and then you define, scroll down, why isn't it scrolling down? A query here. So here I'm doing average CPU over that particular metric that we're focused on, but there's something interesting going on here that I want to call out. So remember, SQL instance is the tag. I have 2 SQL instances, right? And what we can do here is add, this is a wildcard match. It could obviously be a discrete string match, but what it does is it reads this config up here. And I'll show you how this gets drawn in a second. That allows you to do stuff like this and have multiple things in one individual visualization. And so this control here, which is called a variable, is also coming out of the data store as well. So that's dynamically generated. So you don't have to like add SQL 1 and SQL 2 here. And you're able to go ahead and that'll feed this parameter when the query executes for the visualization, so you can scope down to the individual one. So that gives you, we'll zoom out and do it on the screen here and look a little better. The functionality of being able to go across multiple instances. So SQL 2 is there, and SQL 1 is there. And the way that that comes about is sorry, I clicked on something, didn't say it. If you click this gear thing up here, go to variables, you define a variable here, which is the query result from your data source. I'm just saying, you know what? I'm hitting an arbitrary metric that I know that's always going to be there, and then I'm just reading out the server name, which then feeds that value in the drop-down list, right? Cool. So that's how that comes about for here. Did I explain that well, team? We good? All right, yeah. Awesome. Yeah, and so there's one other thing I wanted to cover here. Data source, variables. Oh, yeah. All right, covered all of that. All right. Any questions or comments around kind of the monitoring stack as a whole, right? Good? Anybody running it right now? Doing it, following along? Is it working? Still pulling containers? All right. Yeah, we can look at it afterwards. Awesome. What's next? Not that. Boom, boom, boom. Yeah, I've been using containers for a while, and I still think it's pretty wild that you can do that type of configuration and deployment literally in one line of code. Most of the stuff that we looked at was just looking at config files, literally Docker Compose up, bang, you have that. So I started my research on machine learning. I'm not a machine learning pro by any means, but I did learn though is it's required by like the laws of machine learning to use pictures like that when you talk about machine learning, because obviously computers have brains now. So what is machine learning? I think much to the chagrin of every financial disclaimer ever, where past performance does not equal future performance. Here we're trying to use previous data to predict future data. That's really the goal. I've worked a lot in the monitoring space over the years, and I've worked a lot with vendors in the monitoring space, and I've told them for years, I'm like, you have all of the data about my system. I need you to tell me what's wrong, right? What does bad mean? Bad is bad 87% CPU utilization? I don't know. Because they could go and look at all that data, and then they could tell me, and they could surface, you know what, red for that system is 87%, right? And that's one of the things I've asked for years, and I met with a product team from one of the major SQL Server monitoring vendors last week, and they're doing just that. They're doing these same exact techniques that I'm gonna talk about today in their product to help surface up what's good and what's bad, right? And I'm also gonna show you some of the challenges that we both had in implementation on predicting metrics. So we'll get to that in a second. But other vendors are actually doing this work well on the commercial space. And so we take the data, like we saw, we had a big vector of data for a time series, and we can start to do stuff with that. And once we have that data, we can do what's called fitting it to a model. And so what happens is you feed data into a machine learning model, which is basically just a complex algorithm of stuff that will look at the data, mostly bucketize it, and start to find patterns. And we're gonna focus on that bucketizing when we get into some tuning in a second, because that tuning is gonna be on you, right? Like, wait, I thought this thing was supposed to be like machine learning and like automatic and all that stuff. This is true, right? But the systems aren't solving for general purpose problems, and your workloads are special. That's every customer says that, by the way, their workloads are special. Because also, you have some intelligence about your system. There's a feedback loop that people still have to bring to the party when it comes to what machine learning is. And kind of the big players in the game from an implementation standpoint are Python and R. And I'm gonna let out a little secret. I don't know Python. I didn't know Python until about a month ago. Actually, I still don't know Python because I use Copilot to do all of this. Serious, I did. I was like, so here's the thing. So I had this system cooked up in my brain. I'm like, I knew what I wanted to do, and I drew it all out. But I wanted to, originally I wanted to do this in SQL Server, because SQL Server had a Python interface to work with. And then I was talking to a friend of mine, Joey D'Antoni. He's like, well, that's just a really expensive calculator then if you bring SQL Server to the party just for Python. I'm like, crap, I wanted to learn Python. And so I sat down, I started to write some Python, and I got jammed up on the syntax, right? Because that's what happens. Like, I've been writing code for a long time, and I can usually pick up a programming language, no big deal. But I knew this existed, and I'm like, let me take this for a test drive, and I'll show you like the actual code comments in the Python implementation for this are the actual prompts that I use to do the code. It's bananas, right? So, because I know how to code, I knew how I wanted the data to flow through the system, and so I just asked Copilot to do these things, and it did it. It was mind-blowing stuff. Like, I guess my brain looks like that now, right? I don't know. Anybody use Copilot? It's crazy, isn't it? Yeah. So, and it was, for this implementation, super accurate. I've done some stuff with DBA tools. Not that it's DBA tools' fault, but there is some of the parameters have changed over time. Some of the commandlet names have changed over time. So I'd ask it to do a thing, it would give me an old commandlet, and I was like, But for this, it was like spot on every time. Again, that's not DBA tools' fault. That's just the body of work that they had to look at in GitHub. There's some old stuff laying around. Cool. So let's look at kind of how we're gonna map our system into kind of the machine learning pipeline, right? Generally speaking, you're gonna get data from a thing, and you're gonna cleanse data and stick it somewhere. That's kind of the core thing. And I think a lot of people, friends of mine that are actual data scientists, this is a real sticky area that they spend a lot of time in. We're super fortunate in our platform that we don't have to do that, because the data is very well structured, and it's coming from a single source. And so we don't have to do some of the complex things that they're usually having to do to get the data into a structure and a format that meets what their model needs. And then you go through this process of model training where you start feeding a bunch of test data, darn it, I'm blanking on the word. There's the sample data, and then there's like validation or control data that you also feed. And then you deploy it, and then you get in this monitoring phase where you are looking at the data, and then you're asserting some influence over the data over time, right? We'll look at what parameter tuning from an implementation standpoint looks like in a few minutes. But the idea is it's still up to you to refine how fast or how the machine learning model works. And what I mean by that is this. If I have a data pattern, maybe it's some sort of chart over time, and I want to fit that to a model, the model will make a prediction. And the system that we're going to look at today will break up that system into chunks, and then it'll do analysis on those chunks. Well, how many chunks? Well, that is really defined by the sampling interval. And so that's the parameter that we're going to tune the most today is those chunks, because I want our model to be able to react fast, right? So that's on me to figure out how fast I want it to react to changes in the data set, right? Because we're looking at metrics pretty close in the future, so I want it to react fast. The model that we're going to look at today, or the machine learning system that we're going to look at today, was tuned originally to look at days, month, and weeks. Well, I had to crank it down to look at seconds, right? And so that was a parameter that I had to tune. So what other parameters are out there for machine learning models to use? Well, that really depends on the model, the algorithms, and how that thing's architected. I, as we've already previously established, know nothing about machine learning, right? And so I wanted to solve this problem of doing predictive analytics on a thing. I needed to find something off the shelf, right? I wasn't going to go and write an algorithm and do these things. And honestly, I didn't have the time to do it because I was interested in the outcome. And somebody already solved this problem. There was a project similar to this that was run out of Red Hat a couple years ago to do almost the same thing. But I wanted to kind of just, again, build a kind of a learning prototype for me to expose to our customers and the community about what we can do with these types of things. And so that particular project used a thing called Prophet, which is a time series based machine learning model, right? We know our data is time series. This thing's built to run analytics or predictive analytics on time series data. And the whole point is I feed data into the model and it tells me what's next, right? By default, it does it by day, month, year. But again, we had to ratchet it back to seconds, and we'll get into all of that fun stuff. And so that gives me those knobs to turn, right? So it's tunable, and I don't have to do anything. Like I just pick it off the shelf, I call a library, I feed in some parameters, and it's like, hey, 27, right? And that's what happens in the system. It's available in R or Python, so I chose to use the Python implementation. And the output of this thing is this. I'm gonna feed it in a vector of data, right? Time series data, and it's gonna give me three things. It's gonna give me what it thinks the next value is gonna be, and it's gonna give me an error range of what's normal, right? So a high and a low. And we'll get into all that in a second. It's an open source project from Facebook. So this is something that you can pull off the shelf now. It's a real vibrant and active community on the GitHub repo of people asking and answering really good questions, like actual data scientists, right? So you're gonna have to like right click on the word, copy it, and Google it, and be like, oh, what does hyperparameterization mean? Things like that, because that's the journey that I went through getting all of this. So it's a cool problem domain. All right, any questions or comments around kind of the machine learning concepts team? Good? It's like Anthony cheated and just bought something or got something off the shelf, right? So it fits into our system like this, right? So there's the machine learning Python. We know we got data coming out of Telegraph that's going into Prometheus. I'm going to configure a Python script, or that's going to go and read from Prometheus, a vector of data, run the analytics on it, and then predict the values. Y hat is the term that they use for the predicted value. Y hat lower is the lower boundary. Y hat upper is the upper boundary. And so that's the range. So you get three values out of a prediction. And so if let's say I run a series of data through it, it's going to be like, boom, 15. Or whatever the predicted value is, right? Based on your workload. Right now, it's probably going to land on 61 because I have my CPU pegged at 61 right now, right? And then it's going to give me a lower and upper based off of the span of data that I'm passing in, right? So if I'm passing in 5 minutes of data, well, that's all it's going to use. And this is another thing you have to consider from a cycle standpoint of what you're trying to predict. So in the implementation that you have, I chose 3 days, only because 7 days took too long to run, right, on the system that I had to work with. And so you have to define what the period is that you want to do the analysis on, which is important to your business, right? Because generally they're going to be cyclical in some way. And so maybe a week, a month, a quarter, I don't know what it is, right? But the model itself was built to help Gauge sales over time is a common thing that people want to know. And also seasonality, like am I busy on Mother's Day? Am I busy on Christmas? And taking all of that into account for a system. And so that's what the Prophet was built on. But again, we are ratcheting it down to focus on performance metrics. And so if I get a sample value from my actual Prometheus system that's 25 or 27, I have a predicted value of 15, but I'm in the error boundary, I'm happy, right? Green is good, that's not an anomaly. But what happens if 44 pops out? What do I do? Right? That could be bad. And so that's that's kind of the core behind how we're gonna build the anomaly detection pattern is pull the data out, run the analytics on it, do the sampling with the range, and then look at the value that's emitted by the system. And so let's go ahead and do that together. We're gonna do this in the command line, and then in the next phase, they're gonna package that up in a container and into Prometheus. So any questions or comments around where we're at right now, team? Good? Good. All right. Python. Okay, so we're going to switch to this Python script here. If you are following along, you will literally just, you'll need these three. This will blow your mind. This happened this morning because I added some comments. Copilot's on, and I typed pip install space requests space pandas and Prophet. Those are the actual modules that I needed to install. Like it just did it for me. Right? Cool stuff. All right, so let's launch Python and do some machine learning stuff. Melody, how's the size of the font? Good? Bigger, smaller? Good? All right. So we're going to load a bunch of libraries in. Requests allows me to communicate to HTTP. We need some other system functions around time. Pandas is kind of a data structure library, and Prophet is the library that we're going to use to do the machine learning elements. And we've installed all of those with the pip install at the top there. I've done that. I did that before. Again, not a Python programmer. So this is the actual prompt that I typed in. Basically, like, give me the Prometheus endpoint to query and also get it from an environment variable, which actually I changed that code out. So I have to fix that. So run that there. Here's our CPU query, just straight up the one that we did in the Prometheus interface, but I'm scoping it to a day for here. And then run this code here. If I run request.get, it actually executes the query against the API, which I think is so super awesome. I can do that in one line of code. I get a response 200, but what I want to do with that is I actually want to store that in a variable because I'm going to operate on that. Because inside of there is the JSON structure of the actual data in the response. So I'm going to crack that open, store that in a local variable. We can print that to screen. So this is the actual data result from the query that I can use to feed into other things. So that's just in JSON right now. A data frame is a data structure that holds data. Fancy, huh? And I can feed in the data and add tags to the data structure. And what I want to do here is, if you remember when I queried Prometheus the first time, I had two rows, I had SQL 1 and SQL 2. So in this result is SQL 1 and SQL 2. And so what I want to do here is I want to create a data frame for each of the results. And so I'm iterating over that set, the result set in JSON, and creating two data frames here. And so for each result in the data set, pop out the SQL name, which is part of the JSON response, pop out the actual metric from the query, and then build a data frame, which is just a 2-column array of DS, which is a timestamp, and Y, which is the actual value. Okay, and DS is in Unix time. Y is a discrete value. And then take that thing and append it to an array of data frames. Okay, and then add in some metadata about that so that I know what I'm looking at later. So run that code. What did I do wrong? Run that there, run that there, hit enter, bang, cool. So if I output data frames, which now has 2 data frames in it, you kind of get a sneak peek of what's in there. So I have some tags that describe what is in the data frame. So SQL instance, SQL 1, metric name, CPU, then the data frame and its column headers, and then the first 5 and the last 5 samples. So there's 509 samples in here. So this is the Unix epoch's time. This is the actual value, so 0, idle in the beginning. Things are getting a little warmer from a CPU standpoint now, right? That's SQL 1, and then the same for SQL 2, which is idle. All right, so there's the data. Let's go ahead and we're going to operate on just one data frame now. It's just the demo. We're going to do this like for real in an application in the next demo. But I want you to see what this data looks like in the system. So I'm going to pop off the first data frame, which is the performance metrics for SQL 1. And I'm going to load up a value that's just its predicted name, or the name of the instance and the metric that we're working with. So I'm just doing some data access so that I know what we're looking at. So we're going to predict for SQL 1 this metric, and I have 510 samples. So just kind of draw the picture of what we're going to feed into this model in a second. Okay. So Prophet wants the data, or the timestamp data, in a particular format. It doesn't like Unix time. It wants it in basically a string time, which I'll show it to you how to do that right now. So let's go ahead and do that conversion. And so before, you can see how it's Unix time. If I type df just to access the data frame, Prophet wants it to look like that. No big deal, I just had to convert it. So this is that parameter that I was talking about. So when you instantiate Prophet for the first time, there's a bunch of parameters that you can pass into the constructor to tune the thing. Obviously, you can change the value afterwards too. But this is that change point scale. This is the thing that I had to increase the number of change points, or the chunks that it did the analysis to fit the predictions better to the data. Basically, I'm telling it to react faster to changes, right? Because if I did it with the default and I had it up running for days in my lab, it was so slow for the curves, for the predicted values to come up, because, well, the samples were looking at a whole day of data, and I ratcheted it down to a much lower value. So do that. Then we pass in the data frame that we're interested in doing the machine learning on to fit the model. So now it's reading it all in, it builds the model. The cool thing about this particular implementation, Prophet, is you don't have to save the model. Which means is I can redo this every single time. So I don't have to maintain the state between iterations, which is cool. But as your data sets get bigger, you might want to checkpoint the data, right? But the architecture of Prophet initially was no state between model training, just feed it the data every single time, because you're moving ahead in time, right? You're not growing the data set potentially. You're going to look at a finite chunk, just feed it the chunk, right? And that's the idea. But over time, folks' data sets got bigger, and the compute power to do that was getting to be a little excessive, right? This runs in my lab at work. It runs on a 2 CPU system with 8 gigs of RAM, and it does well, right? So, but it's getting a little spicy when I do 7 days of data. That's why I put it back down to 3. And then for this demo, is back down to 1 actually. And so that amount of data that you feed in is going to turn into real CPU burn when you do these things. So you have to think about that from a scale standpoint if you do want to do this on a larger system. So now that the model is loaded, I can say, you know what? Hey, Prophet, this is a function from Prophet. Give me the next 30 samples at 1 second interval. So give me the 30-second, give me 1 sample for the next 30 seconds. Which means it's going to do that prediction. Why did I pick that value? Because I can only inject, the frequency is going to be like seconds, hours, days, months, and years. And so I wanted to look 30 seconds out. I picked 5 minutes initially, and then I ratcheted it down a little bit because the predictions, I was already sampling at 30, right? So like, I don't know, let's change it to sample interval. And so that was how I got there. And so when I do this, I'll get 30 of those. I wish I could just say 30 seconds and then just get the last one, but what it actually does is it does an array of 30, which we're going to go through that data in a second. So now that that's configured, I'm going to go ahead and do the prediction, which makes another data frame called forecast. So we have our data frame with the source data. We now have the forecast data, which is another data frame with what it thinks is in the future. And so if I ask our original data frame for the tail, which just outputs the last 5 samples, remember we have 500 and some samples in that frame. And then from the forecast data frame, which we just built, I'm going to ask it for the time, y hat, which is the predicted value, y hat lower, which is the lower boundary, upper, the upper boundary. There's 30 things in here, but I'm just interested really in the last one, because that's going to be the prediction 30 seconds out. So the predicted value is 63, the lower boundary is 56, and the upper boundary is 70, right? So we're good now, like we're green, right? Things aren't bad. This is looking over a longer span of time. So this has been running on my laptop for a while. So I have some data in there, some idle periods. So that's why that range is so wide, because sometimes, most of the time it's 0. And then I light it up and make it pretty sad. And so that's why this range is really wide for this implementation. Cool. What you're gonna need to do, if you're interested in doing this, is the lower boundary, if your system is real idle or your system is real busy, the lower boundary, you want to clamp it to not be lower than 0, because you can get a negative prediction, which means nothing. So just 0. And you can get a prediction above 100, which depending on your source data might be valid or not. And on SQL Server, it's not valid, as we saw that, because the upper boundary is at 100. And then on Docker, we saw that that thing could go to 1,000, because that's based on the number of CPU cores in the system. And so let's make some pretty output, print the screen, what we predicted. So we imported 510 events. The predicted value is 64. The actual value is 61. We have 56 and 70 is the lower and upper boundary. The reason why that predicted value is a little higher is because there's a whole slew of time where I was running this thing at 100%, right? We see it pretty pegged at 61. If I sampled maybe the last hour, it probably would be right on at 62, right? It's pretty solid at its prediction. So any questions or comments around kind of how to get to this point? Good? Yeah? Is this interesting? It's good stuff? Nerdy? All right. Cool. All right. I go to 10:30, right? Okay, cool. Me running out of content usually is never an issue. So now we have data. Like we have predicted data off of metrics. And now I want to be able to kind of package this thing to fit it into the universe of things that we have in our monitoring system, right? And so there's this concept, there's the design pattern called the metrics exporter. And Prometheus makes a client, which is basically a software library that will allow you to basically draw that telegraph interface in code. But you don't have to do any of the HTML programming. You just say make a new metric and stick it in the thing. And then when you hit that page, boom, it draws the page, right? And so we're going to use that same exact design pattern that Telegraph has, which is the design pattern from actually this, in packaging up the prediction stuff that we've done. And so yeah, it defines the interface for the metric output. It also makes a web server, exposes them on the network. It's going to be available normally via HTTP or HTTPS. And so we don't have to do the heavy lifting to build a web server, to put the stuff in the right format, to draw that page. We're just going to consume that library to do those things. And so we're going to stick Prophet in the middle here. It's going to read the data. It's going to then give us our predicted values, which we're going to expose via Prometheus back into Prometheus. Right, so we're kind of building on a loop here. Because we're going to read out metrics like CPU, and then we're going to stick the predicted metrics back in, so that when we hit that Prometheus again, those predicted values are just to be available for us to chart. Cool, good stuff. So it looks like this in the end, right? We use the Prometheus client. We're going to get a metrics endpoint, just like we have in Telegraph, and the same exact structure, but we're going to build this together in code. And so in there, you'll see we'll have the predicted values. So SQL Server, CPU, process CPU, Y hat, right? So that's the predicted value that we're sticking back in. There's 2 of those there for the predicted values. And then we also have the other one, the lower and the upper, right? So this just slides right back in. So now we can just consume this like any other metric, right? That was kind of the core to how I wanted this thing to all work together. So let's go ahead and get our data from Prophet into Prometheus using Python, and we're going to build some visualizations together. Where is my code? Where is my code? Did I really close that? Jeez, rookie. All right, let's clean some stuff up here. I think we're good. Yeah, we should be good. All right, so. All right, so there's another Python script. So what we looked at in demo 2 Python, we walked through iteratively, right? Because I wanted you to see the data as it flowed through the system, right? There's another Python script called app.py, which is the real thing, right? So go ahead and open up this. And in here, it's a little bit more sophisticated than we just looked at, because I'm going to draw the page every time, and I'm going to have a web server that's up and running. We're going to do the things that make this available to fit into our pipeline. So there's a couple more includes at the top here. These are the 4 that we started with. At the top, we're going to bring in Prometheus client to the party and a web server. We also have, I'm introducing an object called SQL instance, which is going to have a name and the predicted values, right? So an array of predicted values that we're going to be able to feed back into a system. So this is just a data structure for me to stick things, so I have context, because I want to make an array of these things. The first function is going to be get Prometheus data. So this will actually read the environment variable from our Docker compose config. It'll read a days back variable, so you can define how far back you want to read, aka how much memory and CPU you want to burn. And then our query. I haven't generalized this out to all metrics yet, but I think it's a pretty trivial exercise to parameterize that and pull it out and then feed in which ones I want to do predictions on, right? And then it's the same pattern that we just saw a second ago. Talk to the API server, convert it to JSON, build the data frames, and when I'm done, I have a bucket of data, aka a bunch of data frames that I want to hand into our prediction pipeline. And so this get prediction function just gets a bucket of data frames from the one at the top. It creates an array of the objects that we just introduced. And then for each data frame, crack open some metadata and then run our prediction on each data frame. So if I have 1 SQL server or 10 SQL servers or whatever metric it is, it'll just iterate over that set, generating all the predictions, okay? And then I have it doing the clamping of 0, 100. And then I build the metric name. And I take those metrics and I stick them back in the object. And then I add them to a list. And I just have some debug code output here. So what I'm left with here as a result is a collection of objects with a name and the predicted values attached in there, right, as a data frame. And then this is the part that converts it into the web interface to be consumed by Prometheus, kind of the Prometheus client pattern. And so once we have all of our predictions, what this code does is the very first time you hit the page, it creates the metric objects, which basically is the object that will be updated with the values. So we create a bunch of objects. In this case, it's going to be our predicted metrics. And then we populate them with data. Again, don't worry about the code, but just the process is what I want you to think about here. And then on subsequent page loads, we're just going to update the data because I've already have a collection of objects. On the first page load, second page load, just hit me with the new samples, right? And that's what we're doing here. Let's hit it with the new samples. And then the bottom here is a bunch of syntactical gymnastics to start a web server. It still blows my mind that I can just like in one line of code get a web server after all the years of like configuring Apache and IIS, right? This container thing is like, it's gonna catch on, I promise. So that's what we have here is we're starting up our application. If I hit /metrics, so this is back to your question, Joel. If I hit /metrics, run everything. Just go get the data, run the model, output the stuff, and then return 200 OK. This is if you don't pass in /metrics, you get that output there. And this is the port that we're running on. Again, I could probably parameterize that out to make that a little bit more better. But that's what we have in the app. Then we're going to look at how to get Python under control. There's this thing called requirements.txt where I can list all the modules that I'm using. So when I build the container, it's a much simpler configuration line to install a bunch of Python modules. And if we look at our Docker file now for what we're doing here is I'm coming off of a Docker container that's Python 3.1. I'm copying in that file. It's just a list of the modules. And then I run pip install requirements. So I don't have this big, long, complex thing. I can just pack, if I need new modules, I just throw them in the text. And this doesn't have to change. I copy my application in there. I tell it what port to expose, run Python, boom. I put this in a container now, right? Because we have to, it's a container. It's modern applications. So back to our compose file. what I overlooked earlier was this. So metrics ML is kind of what I called the project. I'm going to build the Docker file that we just walked through. And here's some configuration that we're ingesting. Remember, I plucked off a couple environment variables when I was walking through the code. And so I can dynamically change the Prometheus endpoint and then how far back I want the data to go. I don't want this container to start until Prometheus is up and running and it runs on port 8000. So go to Docker PS. And we can see, there it is, up and running. It's been up for about 3 hours on port 8080. One of the things I did from a system standpoint is I'm outputting, like most Docker containers do, I'm writing the standard out, and I'm also writing when I do predictions out, just to have, because I like output. That's what it comes down to. I don't want to have to go into Prometheus and pull this all out. So I write the console, and I do all the other stuff of sticking it into Prometheus. And so if I go and I access my URL on the base URL, I just get, I get that page. If I put /metrics, I get the predictions. If I go down to y hat, we can see all of those predictions there. And so those will come. And so each time I hit that page, it's running all that stuff. So it's pretty peppy to go through all of the gymnastics that we just talked about, right? So there is the predicted value, 23, lower, and upper. Cool. Yeah, so have a couple other ways you can access it here via the command line. And this I wanted to call out just how fast it is. Like I did that a second ago, but let's get it ahead of myself from a presentation standpoint. But you can see we're talking about, not a very long amount of time. So remember those scrape jobs that I overlooked earlier? This is how we're going to get that data back in. So if I open up our Prometheus config again, where we're getting the data out of Telegraph, I just wanted to slide into that same design pattern, and then boom, I'm sticking the stuff back into Prometheus. Job name is this. The scrape interval is 30 or 60 right now. Timeout is this. Metrics, and then this is the Docker Compose service name on that port. So now it's hitting us every minute, pulling that data in. Pretty cool stuff. If you change this value for whatever reason, you just have to stop and start the container for Prometheus if you get it to that point where you want to play with that. Now, if I go back into Prometheus, and these were already there earlier, but if I type in y hat, there's our values, right? Getting put into Prometheus so we can go and we can query those for all of the things. And then in Grafana, let's look at what that winds up looking like. So there's another dashboard that's automatically loaded for you, which is this one. So clearly my workload finally stopped. And we learned that we can scope this to a particular system. Let's zoom in on that range and talk about what's happening. Go even closer. So in this output here, come on, a bunch of stuff going on. We have the actual value, which is that. We have the predicted value, which is that. And so you can kind of see it stair step each time the model runs, right? And as it gets more data, it gets more accurate. And then when the workload stopped, again, it starts to react to that. And so there we see the actual workload spike up. We see it start to learn from what it realizes is now normal. We get to a phase where it's a little bit higher. The predicted value is a little bit higher than the actual value, about 10%. But again, that's probably due to the previous times where I had it burning at 100%. And then we see it dies and it starts to pull back down. This is where those change point parameters come in, and how, when I say how reactive the model is how fast it'll pull down. I don't expect the model to deal with the fact that it just plummeted to zero that fast. That would be not realistic, right? Because it's looking at such a wide set of data. And so I would not tune for something like that. I'll talk about how I would handle that anomaly when we talk about alerting in a second. So it's pretty neat, isn't it? Let's see. Where am I at? Yeah, we're good. All right. Boop, boop, boop. So let's talk about what the data means and again, why I did this. So here's a chart that I built with no data, right? And I bang it up to 100%, and then you can see the model starting to figure out what's going on. Yellow, predicted value. Orange is the upper boundary. Blue is the lower boundary. But we can see it just takes time to get there. And so I have a larger set that we'll look at in a second. But what I want to focus on, so actual value, predicted value, or upper boundary, predicted value, lower boundary. It's like I got ahead of myself here. So where are the anomalies? Like where would I be concerned in a chart where I had some values? Like when is too low too bad? Like when is it not a good thing? Something's broken, right? Maybe an application is no longer hitting a server to drive the workload. The other way I like to talk to this is if you've decommed a system, right? Now you have proof that the system is decommed. It is no longer doing the workload that we expect it to do. And obviously too high makes sense, right? Too high is going to be when I have a workload and it's changed. Like a database land, that happens a lot, where I'll get an inflection point because something changed and I'm burning through much more data than I thought I needed to do. And then we already walked through too low. So here is a real chart of a workload that I had running in my lab that was intentionally spiky because I wanted to show how the model is able to deal with the longer pattern, but struggles with the spikiness, right? Even when I have the parameter for the model tuned to react as much as it possibly can. And so that's where what we see here. So this first one, it started to figure this out. Like if I went back and looked over multiple days, it figured out every day at 6 o'clock, things got spicy. But it doesn't really pull up to real workload until about an hour later. And so what I was starting to think about is this the best way to handle those kind of workloads? And how do I build intelligence around that? Like, what does that mean? And so I think like these shorter spikes, obviously I'd want to ignore, right? Because there just means somebody did a thing. But this longer sustained spike, the one that's got the arrow to you right now, maybe that's more interesting to me because that's about an hour's worth of work. And so what I realized is that if I'm going to build an alerting mechanism on this, I can't build an alerting mechanism that's going to react just when I'm out of boundaries. I need to build a delay. Oh, I'm out of bounds for 20 minutes. Now I'm going to trigger an alert. Because we're talking about trends, right? We're not talking about, am I at 100% CPU? No, am I deviating from my normal workload? Maybe somebody just did something stupid there, and then I want to know what happened. Then, if I have a actual or a predictive value that is an actual value that is so far above the upper boundary, maybe 20, 30 minutes, then I fire the alert. Hey, something changed in this workload. It's something smells funny, go look at it. And then similarly on the bottom, these bottom spikes, I'm probably not going to do anything with these, right? That's just part of the workload being really choppy intentionally. And a couple more examples at the end there. Yeah, so delayed alerting, I think, would solve this problem. So if I was to build an alerting mechanism on this, I probably only focus on that one in the middle, right? Where I'm out of bounds for an extended period of time. Cool. All right. So what's next? I think I'm going to spend more time tuning that model and figuring out how to make Prophet do its thing. That vendor that I was telling you about, they started with Prophet and they shifted away to another model. I think this is where I think I can get this thing to be a little bit more accurate. I want to generalize the project towards all metrics, meaning obviously we just did CPU from a demonstration standpoint today, but I want to be able to handle all of them. But then that becomes a compute problem. I have to deal with that. So I'm going to have to look at things like memory management, checkpointing the model, right? Because maybe I want to have larger sets of data, and then also parallelizing it. That code wasn't parallel, it was serial when I'm going through these metrics. And so if I want to take advantage of a modern computer system, I definitely would need to parallelize that because it just needs to run faster, but that code would be a little spicier to work with. I'm going to go into the alerting stuff and kind of dig into that to make sure that I'm doing the right things at the right times. Cool. So that is a wrap for all of this. Go ahead and just open up for questions or comments, team. What do you think? Yes. Yeah, that makes sense. Yeah. Yeah. So the comment is, if it's hot for 10 minutes, the inverse of that is maybe back off and have it be cold for 10 minutes. No, that's a good point.
Does Prophet give you the opportunity for predicting into the future?
So by default, the model starts at day, month, year. And so I had to tune it back down to do it such a low interval. So if you go look at the docs, most of their docs focus on annual sales cycles or monthly sales cycles, looking at larger sets of data. And so I had to take it and bring it back down to focus on a real narrower set of data.
Are you still able to have that, per minute or 5-minute precision, but project further out like that? Or
Yeah, so the cool thing about the model, when I say it was automated, is this. I didn't have to tell it the sample interval. It figured out the sample interval automatically, because the sample interval is how frequently we're hitting telegraph to pull out the data, which is 30 seconds. So the granularity that you feed in, it automatically figures out. So if your sample interval is 5 minutes, you'll have 5 minutes, but it also gives you a parameter. If I feed it 30-second samples, I can also say, I just want you to look at 5-minute samples, and I can adjust the granularity based on what I think is important, right? And that also is a performance optimization too. If I have all this discrete data with lots of samples, if I want to make it faster, the easiest way to do that is sample less stuff, right? And so you can pull back into granularity. That's a parameter when you create the object. When I was remember I had profit and the change points 1.0. So that's another parameter right there to handle that when you feed the data in. It's a good question. Yeah, that's a good point. So Kevin's comment is adjusting the prediction not just to a lower interval, but expanding that out to a wider interval to look at bigger periods, right? Yeah.
both of them
On a chart. Yeah.
one across the other. There's enough.
Yeah. No, that's a good comment. Yeah. Cool. All right. Thanks, team.